Okay, so let's continue with file system implementation. So what does it take to for the OS to create a file? Well, first, OS has to allocate a new file control block, FCB, right? And for the file control block, it has to update the directory structure. And to update directory structure, well, you need the directory structure in memory if not already. So it checks, are you in memory? No, I read it from memory. Or if it's in memory, okay, great. Then it updates the directory structure. Why? Because the file has to be created in the context of a directory, right? So give it a name and then which file control block it is. And then now it always can only update it in the memory structure, but it has to keep it in sync, right? So then it has to flush the changes back into the directory structure on disk, right? And so when does it do the flushing? Well, it can do a couple different places. Of course, on file closing, yes, it has to do that, but it shouldn't wait too long before it flushes. And sometimes there's a delay. That's why, like in different systems, you already have a file created, but it might not show right away. And then, like Windows has a refresh. Like you have to refresh it, then you see it, right? It may have a lag. Why? Because it's not being too aggressive at flushing these changes in the directory structure. Right? And only when it gets flushed and reloaded, then it shows in the user directory. So directory implementation is important in a file system. So how can you implement a directory structure? Right. So well, you can do a linear list. So like when you type ls, right, you have these names that show up. And you can keep adding names, deleting names. If you use a linear list, it's okay. That's like using an array, right? And with the file names and pointers to data block. And so the issue though is you have to do if it's whether you use a linked list, it's a linear structure. Poor search performance, right? Because worst case you have to check everything. Now you say, well, I could just keep it sorted, right? Yes, that's assuming you keep things sorted. Or you can use a tree structure, but tree structures take up a little bit more overhead, right? But even the tree structure is no guarantee. You have to keep the tree more or less balanced. So like a more balanced tree, red-black tree, B plus tree. I guess red-black tree is more for theoretical, but B plus tree tries to keep it balanced. And you can use a hash table, and so you've seen hashing several times already. Right, and if it's has collision, then you do probing and link them that hash to the same key. And so now, allocation is an important problem in that you want to be able to create files and delete, so reclaiming after allocating, and also directory structure may need to be expanded on, or as you're working on a file, especially for writing, you may have to allocate as you write, right? So just how much space do you give to a file? So there's different schemes called contiguous allocation, linked allocation, and index allocation. And so it's not only the space, but also the bookkeeping space, okay? So contiguous allocation, how do you do that? Well, a lot like memory, you want one contiguous chunk of memory. Here it's one contiguous chunk of blocks. So when you create a file, they're physically contiguous on disk to a large extent anyway. You have bad sectors, but then, okay, those are skipped. Still, after skipping, they're still mostly contiguous. And then, that way, at least in logical space, you can do the starting plus the offset, right? And so how do you do that? Well, if you have the byte address or byte sequence number, you take that divided by the block size. And if block size is 512 bytes, then what do you have? A quotient and the remainder, right? So the quotient is essentially the block offset, and the remainder is the offset within that block, right? So easy, or displacement into that block. So for contiguous allocation, you use it almost like an array, right? It's best performance in most cases. Why? Because assuming you have such a file, you want to do random access. Well, calculate the starting address and the offset, a lot like how you do memory. But the problem there is just how do you find contiguous space that big, right? So if all your files are tiny, then no problem. But if you have big chunks of various sizes, then that may be an issue. So finding space, contiguous space, that can be an issue. And also, you should know the file size in advance. But do you really know? I mean, you might start out with a little document, only a few words or some outline. Later, you start adding images, you're adding multimedia, like your PowerPoint, you add video clips, you had lots of things. Suddenly, it's several hundred megabytes. How is this supposed to know, right? And every time you add something new, can it even have that much contiguous space? And most likely, you have to move things around a lot, and that costs you a lot of performance, right? And so what do? Well, you could give these large chunks to each file in advance, but that's poor utilization, and you have external fragmentation, right? And so it relies a lot on compaction, but that's still costing something. That's not free. So extent-based file system would be a way to do contiguous to some extent, but then try to string them together. So you have a starting block number and length. So it's not just a block. A block is really just for the transfer, right? But still, you can get a bunch of these blocks at a time. So an extent file would be essentially a linked list of these extents, right? So now this is used in a replacement for Unix file system called Veritas, and now it does have some advantage of contiguous, but only within that particular extent. It does have fragmentation, internal and external. Linked allocation would be one where a file is a linked list of blocks. Now, each block actually needs to reserve some space for pointer to the next block or pointer to nil, right? So that means it's a tail. And so the way you do it is, again, if you take the address divided by the block size, you have the Q quotient and R. But Q is only the number or the sequence number for the block, but that doesn't correspond to the actual just an offset from the beginning block number, right? Because it could be all over the place. And so what if you want to do random access? Well, if just a straightforward link structure would not be very efficient. Why? Because in order to go to the nth block, you have to follow the links. And that means reading so many different blocks just to fetch one pointer. That doesn't seem like a good deal, right? So that's linked allocation could work, but you have to do something about these pointers. So pointers residing in block is not a good idea. But still, that it was what a straightforward implementation would do, because the blocks may be scattered all over the place, and you need to go to a block in order to fetch its next pointer. Right? So for memory, it's not an issue because memory access is fast. But I remember transferring a block that takes a long time. So linked allocation can be flexible. I mean, it's really taking the linked list idea is good for sequential access as long as all you do is sequential access. But the problem is, well, a couple problems. One, what if you lose one of the links? Well, you lose the rest of the file, right? Because if you don't have a way to get to the next, you can't even fix it, right? So you only go from beginning up to the point where you lose that link, and then the rest of the file can't be retrieved. And also random access is really its main problem, right? Random access means you have to follow so many links, performance really suffers. Yeah, because you imagine you want to get to, you have to read this block just to find this next, right? You have to keep following, and then it's not worth it, right? Rereading a whole 512 byte just to find a 4-byte pointer or 8-byte pointer, right? That's not worth it. So a clever way is FAT, file system. FAT is a funny acronym. I always chuckle when I see FAT, 16 FAT 32. Anyway, FAT stands for File Allocation Table. Okay, in case you didn't know. So how does that work? Well, I mean, you must have seen this or used some of this. It's used in original Windows, USB drive, MS-DOS, and was actually FAT by default was a FAT 16. Because it was using these 16-bit quantities. And so how does it work? So instead of spreading these links as part of your blocks, it says, why don't I collect all the links and then put in the beginning, put in one table. That way, when I want to follow all these links, easy, they're already in one place, right? So that way, so instead of like before, like here, right? This is a block, and then the pointer either beginning or end. I collect all of them, put them in this FAT table, right? And so that way, if I know the beginning, I just have to look up that table, right? This FAT. So beginning, okay. So the directory structure says, okay, the starting block for this file is 217. Where do you look in 217? You look in the FAT, right? The file allocation table. 217. So what does this contain? That means the next block number. So you go 618, you go there. Do you have to read another block? You have to read block 217 just to find 618? No, because it's in one structure. All the pointers are in one table. So you index. This can fit in the table very nice, in an array or some other structure, right? So you just index. You don't have to read a block just to get its pointer. All the pointers are collected together at the beginning of this file system, okay? So that way, if you want to do random access, what do you have to do? Yes, you still have to follow the pointers, but now you don't have to load one block just to get a pointer, just to follow it, just to load another one, just to follow it. You just go in memory. So hopefully that's much faster. So theoretical complexity is still linear, but practically you're hundreds of times faster.
So this is a table of pointers.
Yes, that's what it is. Pretty clever, huh? And simple. Why wouldn't you want to do that? Right. So, and FAT32 just says, okay, 16-bit pointer not enough. Let's go to 32-bit. Okay, but same idea. Okay. So at the beginning of the volume, it's a table with all these links. Okay. I think it's kind of clever. So simple for new block allocation. Well, why it's that table. It's just there. You just update it, right? And then it can be cached. That's actually the whole point. But the problem there is with your non-volatile memory, especially flash, because it's always at the beginning of your volume, and every update you have to rewrite over the FAT. Guess what gets worn out? Well, the FAT gets worn out very quickly, right? And so unless you do some weird leveling, you probably don't want to have to. You don't want to rewrite in place anyway too often. Otherwise, it can be a problem. Now, of course, these are more reliability issues than anything else. So if a fat is corrupted, then yeah, you lose links. But then you could try to construct from the other ones. Now, index allocation is something that, like, you can say it's almost like a mini fat, in the sense that, well, because that's what the index table is, right? You can think of a fat as an index table. In that you, so basically it's a table of pointers to its data block. So fat is for the entire volume, right? You have one USB stick, one partition, one fat. That has everything on there. But index allocation says, well, I don't want to put all of this stuff in one giant table. Instead, per file, I might want an index or index table, right? And that way, a lot like how your page table works, right? You one process, one page table. Here, one file, one index table. So think of it as a mini fat, where in that array it points to the block number, the next block number. So you index into it, and then that way you can just go. So it's unlike fat, which is really for the entire volume. This is for file per file basis, right? So I just have to say my block number, index into it, and then that gives me the pointer, right? So it doesn't rely as much on, say, tracing. So in fact, for random access, this may be even faster, because once you have that index, I can go to any block I want, right? And I can find out whichever block I need, and then just fetch that block, right? So index allocation more efficient for random access, right? Because all you have to do is look in the table, and no external fragmentation. Although you do need the space for that index. Easy for file creation, right? Because that way you have, as long as you have one index, then it can point to any block. However, the index, just how big is this index table supposed to be, right? Remember, one problem with virtual memory page table is these page table get huge, right? And here, the index could also be huge. And just how big do you want to allocate it? Unix came up with a clever way. It's a lot like your page table, which could be hierarchical, right? Second level, third level page table. So inode is the Unix structure for it. So it is kind of a hybrid. So it does have the fixed number of index entries for your basic one. And if you need larger, you go to the secondary or third level, right? So anyway, back to index allocation for a second. So this is an index table for a file, and from there I then can do this like the index in here, and then it has these. What I can do is, instead of tracking the absolute block number, it could be relative, right? So, and or it could be -1 here is like a nil, right? So that means non-existing. So 9 points to 9, 16 points to 16. So if you want, say, fifth block, 0, 1, 2, 3, 4, 5. Well, it's nil. But third block, 0, 1, 2, 3. So you just, once you have this index, you just go directly and fetch block 10. Okay, so that's fine. And if it's -1, nil, that means it doesn't exist. So for index allocation, as long as you have the access to the index, yeah, it's pretty quick. And so now for sizing, so suppose your maximum file size is 256K, which is tiny by today's standard, but okay. And block size is 512 words. Then, well, each so you can the index table in exactly one block, right? If you do work out the math. So, but then 256K seems small for maximum file size nowadays. Now, if you do block size of 512 words, then assuming word size is large enough to fit, then the link scheme, the link block of index table would, well, that means if you can do additional entries as a link scheme, then that way there's no limitation because you can just go keep linking, and each time you have more entries. Okay, and now two-level scheme is one where a lot like these page tables, right? So you, if you have 4K blocks, you can store these 4 byte. You can store 1K of 4 byte pointers in the outer index, and so that allows you to have file, basically about 1 mega, a little over 1 million data blocks, and file size of up to 4 gigabytes. Now Unix is this combined scheme in that you do have direct blocks. So first it's file metadata, so that's your traditional file control block, right? And then followed by the direct block. So instead of a single pointer, it has 12 direct entries. So if your file can fit in the 12 direct entries, great. All you need is one inode, right? And that way, and random access within this small one is easy because you just index and then you can get. So direct size is what? If it's 12 entries, so assuming you have 4K blocks, so 12 times 4K, anything 48K, all you need is one inode, okay? And then if you need anything larger, well, you can put the additional ones into the single indirect block. So what that does is then it is a pointer to one index, right? And that index should fit within one block. Because we said that if it's a 4 byte pointer, right, and then 4K block size, you can have 1,024 entries, 10 to the power 10 entries, right? So that way you can have additional entries in here. So in addition to this, you can have more here. So that allows you to have 48K plus additional 4 mega bytes of your single indirect entries, data, right? Because it's 4K times to the power of 10. Now, if 4 megabyte is not enough, then you can go into double indirect and even triple indirect, right? So double indirect means it goes to one index, but these index point to additional blocks. Each one is an index, right? And then the actual index, so in the second level. So each one is to the power of 10 entries, and each one is 4K. So then if you go to double indirect, then it's 48K plus 4 megabytes plus 4 gigabytes. So, and then you could go to triple indirect, and that's going to be really, really big, right? And so that way it's progressively increasing the overhead as your file size gets larger. But by that time, your overhead, I mean, you wouldn't care as much about the overhead when your data is so much larger. So this scheme scales well. Okay, and that's kind of the same thing. Okay. Anyway, so for performance, well, file system performance is important, and so you want performance to be good for sequential access in some cases, for random access for other cases. Right? And random access is also called direct access. Now, if you have a linked structure, well, certainly it's good for sequential, but then random will suffer. Now, OS usually takes some kind of hybrid approach. So if it's contiguous, therefore, if you want direct access, then it presents a contiguous scheme, and if it's sequential, then linked scheme is fine. But how do you know in advance? Well, OS doesn't really know in general, but then there are ways for the OS to guess or for the API to give hints. And so it may support some kind of API to say, well, I want to create one that's contiguous, one that's linked, and OS will try its best to do it. Or if it can't, then it offline or during idle time, it does the conversion to optimize for the performance. Or it could do it from its own profiling. Now, index scheme is potentially more complex. Just pure index scheme, indexing scheme. Why? Because then, if you don't want to do a single block access, well, you would need to fetch the index block, find out, then you fetch it, right? Of course, the assumption is you can cache this, just like a fat table, right? So that way it helps. And also clustering can help improve performance. You remember clustering, right? We talked about this in memory allocation, and the same thing works with these disk blocks as well. So that means you can use one. Remember, there's one of the page table scheme is that it's a clustered table scheme, right? It's the same idea, so that you put these. You remember the page table. You use fewer bits to hash or to find that cluster page table, and the same idea applies here. So that way you can rely a little bit more on the physical proximity of these blocks, or logical proximity, so that way you don't have to load as many different such index tables. Now, so hybrid index and contiguous scheme would then means the OS can have the option to restructure your file beneath it. To you, it doesn't make much of a difference, other than hopefully the performance is better for your access scheme. Okay, free space management is an important task that OS has to do. So just like memory or pages, the OS for managing a file system has to keep a free list. And this structure, the difference is this structure has to also be kept on the disk as well. Okay. And so how can you do it? Well, so you can use a bit vector or bit map or some other status map array. And you could use a linked list. I could use grouping or counting. Right? So bit vector would be you use a smaller structure to indicate the state. Is it allocated? Is it free? Right? And now you need to do it for the blocks. And in linked lists for the free space is a lot like the linked linked allocation. Grouping would be linked index allocation, and counting is a lot like the contiguous allocation. And so the OS usually manages these free space same way as a file. So now bit vector, you have to be given a block size and then also disk size. Then that determines how big your bit vector needs to be. And so like this, how many bits? Well, in this case, you do the division, you get 2 to the 28 or 32 megabytes. And you can do clustering to save the size, right? So that way it can be 8 megabytes of memory. So for a 1 terabyte, yeah, that's actually not too bad. And easy, this scheme is easy to get contiguous file. Why? Because you just have to examine contiguous zeros, right? And then work out the size. But of course, based on the actual allocation, worst case, you still have to visit everything. Right? What's the con? Well, the con means that the bitmap must be cached for performance, right? And I mean that we've seen that several times. And 1 terabyte disk requires 32 megabytes of bitmap. Is that big? Hard to say. I mean, to me, it's okay. But oftentimes you need to keep track of more than just 1 bit, and that's where it starts to grow quickly. Now you could also have the link to a free space list on disk. So remember, for allocation, your block can have pointers to follow. Well, you can do the same for the free space as well. The link is in there. Might as well use it to link to the next one, right? And so that way, there's really no wasted space and no need to. And it does. It's actually a little better than the other parts, because if you want some free space or some free block, that's okay. You don't have to do any random access. You just pick from the beginning, right? Or if you have a tail pointer, you can pick from the tail. And it's because the idea here is any block is as good as any other block, right? And so you don't have any need to traverse the entire list. And in fact, you could even use a scheme similar to FAT to keep track of your free block space. However, you can imagine the problem with this is, how do you determine the contiguous space, right? It takes a lot more work to allocate, because you could take this, but then you have to then essentially do what the reconstruct that bitmap, and then find out the contiguous free space. Now, grouping and counting in linked lists or linked free lists. So grouping, basically you need to modify the linked list to store a first block, and then have an index structure or something similar to an index structure. Then point to these free ones, and so that way, so the mechanism and everything is very similar. And if you need more, you can have another link to another index. Now, counting would be to keep the address of first free block and count the following free blocks. And the free space list then has the entries containing the addresses and the counts. Now, there are newer mechanisms for these devices, storage devices, to help. So storage devices want to be able to do some optimization so that it can improve performance, and oftentimes and not a whole lot other work. And so this has been the case for both hard disk drives and for non-volatile memory. So for ATA hard drives, there's what's called trim commands, and for non-volatile memory NVMe based, there's unallocate command. So what these do is the OS sends commands to say, well, I would like to unallocate, or I would like to free these blocks or mark them as free. Now, does the storage device actually do it? Well, it at least does the bookkeeping. Does it erase it? Probably not. And why would it do that? Well, in a way, it's somewhat lazy evaluation. In other ways, it's a scheduling issue. So it wants to do it at a time of convenience, and in fact, you may want to group several of them, do the erasing or do the free space reclamation together, so that it pays less overhead, right? And the OS shouldn't have to worry about things beyond a certain level. So Now, so efficiency can depend on a number of things. It could be the disk allocation, the directory algorithm, also the type of data kept in the directory entry, something called D entry for directory entry. And so, for example, a lot of these file systems also keep track of like the last access date, last modified date, right? So that means even if you just open the file, it has to update the metadata. Say, oh, this was last opened on this day, this time, this, right? And for writing, sure, yeah, you already have to touch this disk and update. But then for reading, even if you're reading a byte, just a byte, or then yeah, it has to. I mean, at least logically speaking, it has to update it. Now, when does it actually make the update? Well, that's a separate question. But conceptually, it has to. Okay, and metadata structure allocation. Do you need to pre-allocate something or as needed? Okay, so that some of the trade-offs may be similar to like demand paging. So for example, you have like a directory, right, or you have index schemes, right? Do you pre-allocate these? There's a space for these, and if it's directory, right, do you pre-allocate a bunch of these directory entries because suddenly the user creates 3,000 files, right? Or do you do them on demand? For demand paging, it may be a little easier because you operate at memory speed, and especially if you don't have to load anything, you just have to initialize the page content to 0. That's great. But disk is so much slower, right? So some pre-allocation may be helpful to reduce that latency. Now you can do fixed size or varying size data structure, and so FAT16, it's fixed size. So the maximum size of each partition works out to be 32 megabytes, right? So what if you have a larger file than 32 megabytes? Well, then you have to split them up, and in fact, you can put anything more, and then you need some other tool to then string them back together. Now, FAT32 raises this file limit to much larger, to 4 gigabytes, and then you have a maximum of 16 terabyte partition size. Although there's some tricks to get beyond the 4 gigabyte per file limit, if you try to look it up. Now, performance also depends on whether your data and metadata reside close to each other, right? So if they are far away, that means you actually do very distinct disk access. Whereas if they're together, they may be accessed together, and you save overhead on, or save the latency. So their concept of what's called buffer cache and page cache, right? Page cache we've seen in virtual memory. Buffer cache is really more for these disks or for file system. So now buffer cache is done very often as part of main memory or kernel memory, and it's really just for whether you're doing prefetching or most recently accessed blocks. So that way, when you do I/O, you're actually doing it to the buffer cache. It doesn't always go through to disk. You may wait until some time when it's convenient, when they can consolidate a number of these disk accesses together before it does it. Okay? So without this buffering, that means every write must actually go all the way to the disk, and before you can be sure, right? And that's costly. Now, page cache is for paging, right? So buffer cache and page cache, both are caches, both take up kernel memory. And there's actually somewhat related concept. Why? Because if you do paging, you're also doing it to disk, right? And the size of a block is actually the same. So do you do separate buffer cache and page cache, or do use the same mechanism for both? Right? That is actually one question. And what kind of optimization can you do to improve performance? Do you use synchronous or asynchronous API? And also, are there things you can do specifically for sequential access? Okay, so let's take a look at buffer cache and page cache. If you keep them separate, then you could have what's called double caching problem. Why? Because, say here, you are doing memory mapped I/O, or you're doing the I/O using read and write. Right? So if you're doing I/O read-write, what happens? Well, the OS says, oh, that's disk operation, so it just accesses the buffer cache, right? And then file system. Now, if you're doing memory mapped I/O or in conjunction with paging, then it's handled by the paging, and so then it goes through here, and but then because the page cache itself may also be associated with concept of disk block. Then OS says, oh, that looks like the disk, so it caches it for it. So that means the same data gets cached twice, but once in buffer, once in page. Okay. And that way, it's not good use of the memory resource. And so if they're not aware of each other, so the better way to do it is with the unified buffer and page caching. So in the unified scheme, what happens is then this buffer cache actually handles paging as well. So any memory mapped I/O also comes in here. I/O rewrite also comes in here. Right. So that way, the same page cache or same buffer cache is used for both, depending on, because they're the same, right? And what does that mean? That actually means the virtual memory system will now have to be more complicated. It has to manage the file system metadata and the file system data. And so the purpose is to avoid double caching, but it leaves a few issues open. So which cache gets a priority, and what replacement algorithm do you use? Now, so for optimization with page cache for sequential access, so sequential access allows you to optimize more. Also, if you're doing page cache. And see, remember the concept of cache is to exploit locality, right? Temporal locality, spatial locality. The idea, at least with the processor, is that if you access some data, you're likely to access it at the same one again soon, or you're likely to access data nearby soon. If it's nearby, then it's called spatial locality. If it's the same data then that's temporal locality, right? And so now here you want to do page caching, but if it's sequential access, then what happens? That means you probably don't want to use LRU. Why? Because the access pattern is such that you go down the sequence, maybe just a couple times, but you march down the sequential data. And if you do LRU replacement, then what happens? It only kicks out least recently used. And whereas the more recently used, well, according to the sequential access pattern, you're probably not going to use it again anytime soon. So replacing the more recent ones may actually be a better idea. Okay, so what are the solutions to this? So there are two ways. One is what's called free behind, and the other called read ahead. So what does free behind? That means if you're accessing within the page, yeah, you keep it in page cache. But if you move to the next page, then you actually free up the page you left behind, so to speak, right? Because you're now incrementing. So the one before it, according to sequential access pattern, is not likely to be used again. So freeing it soon may be beneficial. Another way is what's called read ahead, because you can anticipate a sequential access pattern, and for reading you don't have a whole lot of way. So what can you do? So now you can do read ahead, which is a lot like prefetching for processor, right? Remember processor, if you're executing, then what's coming up next or next page, well, it's likely to get access again. So by reading ahead or prefetching, by the time you need it, by the time you read the next page, it's already in there. So it saves you a lot of latency. So these are the kind of things you can do with sequential access. Okay, another has to do with the synchrony. What does that mean? That means, are you making synchronous call, asynchronous call for reading or for writing, right? Does that make a difference on performance? So now most writes are what's called asynchronous. So that means it's maybe more common, and then it makes use of the buffers in the sense that you issue a write request, and the fact that it has buffer means it doesn't have to actually flush right away. It may accumulate, and then up to a certain point, then it writes. Okay, and so small writes may appear actually faster because it's all done in memory. It hasn't flushed out, or the flushing doesn't it doesn't really happen that much. You don't wait till the flushing finishes. You just keep writing. Okay. Now, if you do larger sequential writes, then probably doesn't make much of a difference anyway, because at some point you run a buffer cache and it already hits its limit, and everything else is waiting on pending I/O to continue. Otherwise, you can't. Now, asynchronous or asynchronous reads, maybe difference is not as much. So they now compared to like asynchronous writes, asynchronous, well, even synchronous reads are frequently slower, right? Because you actually have to wait until the data actually finishes transferring. Whereas write, taking its time, is just buffering up in memory. Okay, and so that this kind of so really for reading, prefetching is what actually helps. The synchrony part doesn't make much of a difference. Now, it's important to keep these on-disk data structures consistent. So what are these structures? So directory structure, free block pointers, and also free file control block pointers. And how do these on-disk structures become inconsistent? Well, it could be a system crash. Could be like you pull your USB stick before it says you can safely remove your USB stick. And why is that? Because the caching basically prevents greedy writes. It tries to be as frugal as possible, so it's waiting until it can consolidate a number of different events, then do it one. Okay. But anytime you have only partial update, not complete update, whether due to crash, due to careless pulling of disk, then you could get into inconsistent data because some part of it is updated, the other part not updated. So for recovery, what can you do? Well, like Unix has a tool called FSCK for file system check, and you can just run it. It'll attempt to repair any data structure also. Now, whatever you do, you have to do some consistency check. So some file systems also include checksum, others include these structures for checking whether your file content matches a particular signature. And also, in the worst case, you always have to anticipate the worst case, right? You want to back up data from disk and so forth.